All right, so this is Unit 1, Lesson 6, Linear Systems. Maybe. All right, so the less essential question is how can you find and represent solutions of systems of linear equations and inequalities? And at the end of this lesson, you're going to be able to use a variety of tools to solve systems of linear equations and inequalities. All right, so our first example is solving a system of linear equations. So in general, we've been using graphing to solve, but we can also use either elimination or substitution in order to solve systems of a linear equation. So what is the solution of the system of linear equations, x plus 2y equals 3 and x minus 2y equals 4? So a system of linear equations is a set of two or more equations using the same variables. The solution of a system of linear equations is the set of all ordered coordinates that simultaneously make all equations in the system true. So basically, when you graph two lines and they meet at a point, that's your solution to this system of linear equations. If they never meet, or they're the same line, they're different. If they never meet, they're usually parallel to each other, and there's no solution, so they're inconsistent equations. Or if they're right on top of each other, they're infinite many solutions because they're the same line. Okay. So I can sketch the graph of each equation to estimate the solutions, then I can solve algebraically. So this is my graph, my two systems, or my two linear equations. I can notice that they meet at a point somewhere between 3 and 4, and then somewhere between 0 and -1. I can use what I know then to solve this system. So basically what I can do is I can graph them using Desmos, or I can solve them. So right now I have x plus 2y equals 3 and x minus 2y equals 4. Well, both of these have a variable of x by themselves. So I can solve each of these equations for x and then set them equal to each other. So x plus 2y equals 3, I subtract 2y from both sides, and x minus 2y equals 4, I add 2y to both sides. So I get x equals 3 minus 2y and x equals 4 plus 2y. I set them equal to each other and I solve for y. When I do that, I get y equals -1/4. I can then take that value of y and substitute it back into one of my equations. Okay. Doesn't matter which one, completely up to you. So they did x equals 3 minus 2y. So remember, y is -1/4. I multiply that through 3 minus that gives me 7/2. Okay. So the solution is 7/2 and -1/4. These values are close to the estimate made from the graph. You can check to confirm that these values satisfy both equations. Basically, you can substitute them in and solve them. So I can actually go ahead and put these on Desmos. X plus 2y equals 3. A little bit, hang on one second. And x minus 2y equals 4. Okay, so here's my two equations. They meet right here at 3.5 and -0.25, which is the same thing as 7/2 and -1/4. Okay. So I can solve this system of equations. 2x plus y equals -1 and 5y minus 6x equals 7. I'm going to go ahead and plug them in. So 2x plus y equals -1. And then 5y minus 6x equals 7. I can see that they meet right here at this point, which is -0.75, 0.5. It's -3/4 and 1/2. I can also solve this algebraically if I notice that y right here is by itself. So what I can actually do is I can solve for y in this first equation and then find what I have and substitute it back in for this y in the second equation and solve for x. So when I do that, I get 2x plus y equals -1 and 5y minus 6x equals 7. I solve the first equation for y. So 2x plus y minus 2x equals -1 minus 2x. So that equals y equals -1 minus 2x. Doesn't matter which order you put it in, okay? I then substitute that information back into my second equation. So 5 times the quantity, -1 minus 2x minus 6x equals 7. I use my distributive property, -5 minus 10x minus 6x equals 7. I simplify, -10x minus 6x is -16x equals 7. And then I add 5 to both sides to get x by itself, which gives me -16x equals 12, which simplifies to -3/4, which is what we had. I then take that -3/4 and I substitute it back into one of these equations. You can use either equation. You can substitute it back into the second equation or the first equation. I would recommend the first equation because y is already by itself, which will eliminate some of the steps that I have to do mathematically. So when I substitute my value, my x value in, I'm going to do it into my first equation. So I get 2 times -3/4 plus y equals -1, which is -6/4. I add 6/4 to both sides. When I simplify that, -1 becomes -4/4, so I can just add the fractions together. -4 plus 6 is 2, so I have 2/4, which simplifies to 1/2. I can do the same thing for 3x plus 2y equals 5 and 6x plus 4y equals 3. So I have, if you see here that these are actually two parallel lines, which means they never actually connect with one another. So there is no solution. These two lines are inconsistent with each other. There's no solution to them. Number 2, solving a system of linear inequalities. So Malcolm earns $20 per hour mowing lawns and $10 per hour walking dogs. His goal is to earn at least $200 each week, but he can work a maximum of 20 hours per week. Malcolm must spend at least 5 hours per week walking his neighbor's dog. For how many hours should Malcolm work at each job in order to meet his goals? Okay. So what they've given us is a lot of information that we need to figure out what we want to do with. And we're going to create inequalities, a system of inequalities in order to help us solve this problem. Okay. So the first thing that we know is a system of linear inequalities is very much like a system of linear equations. So it's 2 or more inequalities using the same exact variables. So the first thing that we want to do is actually pick our variables. So in this case, we're going to use x and y. Those are the most common variables that are used. Are they the only variables that can be used? No, that's generally what we use is x and y. Okay, so x is going to stand for the number of hours that he mows lawns, and y is going to stand for the number of hours that Malcolm walks dogs. Okay. The next step that we have is writing inequalities to model what we've been given. Okay. So we know that he earns $20 per hour mowing lawns and $10 per hour walking dogs. So I'm going to take the 20 and multiply it by x, because that's the number of hours. So the amount of money he makes per hour, plus the amount of money he makes for walking dogs, 10 times y. And I want that number to be greater than or equal to 200, because he wants to earn that much money a week. Okay, so that's my first equation, or inequality. 20x plus 10y is greater than or equal to 200. Okay. We also know in our equation that he can work a maximum of 20 hours, which means he can't work any more than 20 hours. So the x plus y, the number of hours he spends mowing lawns, plus the number of hours he spends walking dogs, has to be less than or equal to 20 hours. Okay. Then Malcolm must spend at least 5 hours walking dogs each week. He has to walk his neighbor's dog, right? So y, the number of hours spent walking dogs, has to be greater than or equal to 5. He has to at least do 5, okay? So step 3 is I'm going to actually graph each of these inequalities, okay? So when I do that, the red one, y is greater than or equal to 20 minus 2x. That's this red line right here. Okay? So that has to be greater than. So anything that's bigger than this red line. The blue line, y is less than or equal to 20 minus x. So blue, and it's going this way. And then y is greater than or equal to 5. The green is going this way. So the part that overlaps here is this part in light yellow. So I can pick any point in here. I could pick 6:12, and that would be a solution. You could spend 6 hours mowing lawns and 12 hours walking dogs. You could spend 12 hours mowing lawns and 7 hours, or 6 hours walking dogs. It completely depends on any number in here in this yellow shaded region would count as a solution. So any point in the shaded region, such as 12:7, which is right here, okay, is a solution to the system of inequalities. So if Malcolm spends 12 hours mowing lawns and 7 hours walking dogs, he will have met his goal. He'll also meet his goal if he does 12 and 6, 10 and 6. So it completely depends on. Okay, so anywhere inside that yellow is going to be a solution. All right, let's try a problem out. I want to graph the set of all points that solve this system of linear inequalities. So the first thing I have is 2x plus y is less than or equal to 14. So when I do this, I want to solve for y, basically. So when I do this, I'm going to subtract x from both sides, and I'm going to divide by 2, which gives me negative 1/2 x plus 5. So this blue line. Okay, so this blue line. Sorry, I'm looking at the blue. So I'm solving for y. So I have y is negative 2x plus 14. So plus 14 is right here. And then negative 2, so I go down 2 over 1. That's my, okay, and it's less than, so it's on this side of the equation. The red one is x plus 2y is less than or equal to 10. When I solve for y, I get y equals negative 1/2 x minus 5. No, plus 5. So plus 5 right there. And then this goes down 1 over 2. Okay, still over here. Okay, so that's less than this one over here. Okay. Then I have x is greater than or equal to 0. Okay. So that is going to be a vertical line right here. And that's going to be over here. So over here. And then the purple is y is greater than 0, so that's a horizontal line at 0. And I needed to have greater than 0. So that means anywhere in here, this orange section is going to be a solution to my problems. It's less than the blue, less than the red, greater than the green, greater than the purple. Okay. These are all going to be solid lines because of the fact that they all have equal signs underneath. It would be a dashed line if it was a less than or greater than sign. All right, solve a system of equations in 3 variables. So there is a little video here I'll let you watch.
How can you solve a system of 3 equations in 3 variables? Part A. What is the solution of this system? You can rearrange the order of equations, multiply the equation by a non-zero number, and replace one equation with the sum of 2 equations, and not change the solutions of a system.
So basically what this means is I can multiply any one of these equations by any number. I can add them or subtract them from one another, and it won't affect what my solution is.
Take the original system and apply these operations to simplify the equations. First, replace equation A with the sum of A and B. The z cancels out, leaving just x and y variables remaining.
Okay, so what they did was they added a plus b. So 2x plus a negative x is 1x. Y plus 2y is 3y. Negative z plus z is 0. That cancels it out. Negative 10 plus 3 gives me negative 7.
To cancel out the z in equation B or C, the coefficients of z in the equations need to be opposites. To make the 1 in equation B opposite of the 3 in equation C, multiply B by negative 3. Leaving equation D as it is, equation E and F can be added together, replacing equation E with an equation that no longer contains the variable z. Now all that needs to be done is apply operations to remove x or y from either equation G or equation H.
All right, so what they did was they added E and F together. That's how they got this new equation H. And then they just kept J down below. Okay. So now what we're going to do is we have two equations that have two variables in them. So I'm going to use what I know and what I can do in order to solve these two equations.
Then the system can be solved. To cancel out x or y, the coefficients of that variable would need to be opposites. Either would be correct, but all coefficients and constants in equation H are divisible by 4, meaning that the 4x can become a negative x by dividing by negative 4. Divide equation H by negative 4. Now equation K and equation L have opposite coefficients of x. Now equation K and equation L can be added together to cancel out the x. Replace equation K with the sum of equations K and L. Now the system is ready to be solved. Solve for y using equation N. Y is equal to negative 2. Next, you can use equation P to solve for x. Substitute in the value of y and isolate x. X is equal to negative 1. Finally, use equation Q to find the value of z. Substitute in the values of x and y and isolate z. Z is equal to 6. The solution to the system is x equals negative 1, y equals negative 2, and z equals 6.
All right, so this is the second example problem. So we have the system of linear equations of 2x minus y plus z equals 3, x plus y plus z equals 5, and negative 4x plus 2y minus 2z equals 0. Okay. So what I'm going to do is I'm going to first notice that, if I do, I'm going to label them. A, B, and C. I notice that if I add A and B together, I'll get rid of the y's. So I'm going to do that first. A plus B. So I have 2x minus y plus z equals 3 plus x plus y plus z equals 5. 2x plus x is 3x. Negative y plus y is 0. Z plus z is 2z, and 3 plus 5 is 8. Okay, so this is going to be 3x plus 2z equals 8. This is going to be D. Okay. I also want to get rid of y. Okay. I do notice that if I multiply A times 2, I can cancel out this y and c. So I'm going to do 2 times A plus c. So I'm going to do 2 times A first. So 2 times 2x minus y plus z equals 3. So 2 times 2x is 4x. 2 times y is negative 2y. 2 times z is 2z. 2 times 3 is 6. And then I add negative 4x plus 2y minus 2z equals 0. Okay, this cancels out. 4x minus 4x becomes 0. Negative 2y plus 2y becomes 0, and 2z plus negative 2z becomes 0. 6 plus 0 is 6. Well, 0 can't equal 6, so this is no solution, and it's inconsistent. All right, so we're actually going to look at an example of x plus y plus z equals 3, x minus y plus 5 equals 1, and x plus y minus z equals 2, and solving this system of linear equations. So we actually worked on this one in class, and I figured out where the mistake was. When I copied down the problem to do a minus b, instead of both of the z's being pluses, I had one as a subtraction sign, which messed everything up. So now it's correctly written down. Okay, always double check your work. So when I'm doing this, I'm going to subtract x minus x is 0. Y minus a negative y, it becomes positive. So this becomes plus 2y. And then z minus z is 0. And 3 minus 1 is 2. So now I have y by itself. It's the only variable here. So I can actually take this, I'm going to make it d. Okay, and I'm going to solve for y. So I have 2y equals 2. Divide both sides by 2. Y equals 1. Okay, now I have one set of my solution. That's great. I need to find the other two. So I have y equals 1, and I want to solve for either x or z. It doesn't matter really which one you solve for. It's completely up to you. I do notice, though, that if I have z and negative z, I can add those two together, and they can get rid of my z's for me, and I'd be left with x, hopefully. So I'm going to add b plus c. When I add these together, x plus x is 2x, negative y plus y is 0, z plus negative z is 0, and 1 plus 2 is 3. Okay. Oh, well, I have x by itself now. So 2x equals 3. I solve for x, so x equals 3 halves. Now I have y, and I have x, and now I can solve for z. I can pick any one of these three equations that they gave me originally, and I can substitute them in for x and y and solve for z. I'm going to pick A just because you don't have to pick A, pick B, pick C, completely up to you. I'm going to pick A. So I'm going to go ahead and substitute in my values for A. So I have, here's my original equation, x plus y plus z equals 3. So x is 3 halves, y is 1, I'm solving for z. 1 I can rewrite as 2 over 2. This gives me 5 halves. I subtract 5 halves from both sides. So I get z equals 3, which I'm going to rewrite as a fraction, over 2, which is 6. So 6 halves minus 5 halves is 1 half. So my solution set is 3 halves, 1 half. That's my solution set. All right, so this is for the second try it problem. I have 2x plus y minus 2z equals 3, x minus 2y plus 7z equals 12, and 3x minus y plus 5z equals 10. Okay, so I can go ahead and label these A, B, C. Okay, so I'm looking at these and I see that y in A and y and c are opposite of each other, so I can add them together and get rid of my y's. So I'm going to do a plus c. Make sure you copy everything down correctly. 2x plus y minus 2z equals 3. and 3x minus y plus 5z equals 10. I'm adding them together. 2x plus 3x is 5x. Y plus negative y is 0. Negative 2z plus 5z is positive 3z. And 3 plus 10 is 13. Okay. So I have 5x plus 3z equals 13. That's letter D. Okay. And I can also notice that if I multiply a by 2, I could also cancel out my negative 2's here, my 2y here. So I'm going to go ahead and do that. I'm going to do 2a plus b. So I'm going to do the 2a first. So I'm going to do 2 times 2x plus y minus 2z equals 3. 2 times 2x is 4x. 2 times y is 2y. 2 times 2z is 4z. And 2 times 3 is 6. Okay? Then I'm going to add b, which is x minus 2y plus 7z equals 12. Okay. 4x plus x is 5x. 2y plus negative 2y is 0. Negative 4z plus 7z is positive 3z. And 6 plus 12 equals 18. So now I have 5x plus 3z equals 18. I'm going to call that E. I can notice that I have x and z's in both of D and E. I also notice that 5x plus 3z equals 13 is D, and 5x plus 3z equals 18 is E, which means these are not going to be, they're not going to have a solution. They're going to be inconsistent. So if I take D minus E, I get 5x plus 3z equals 13 minus 5x plus 3z equals 18. And I'm going to get 0 equals negative 5. Well, that can't happen, so there's no solution. Example 4 says write a system of equations as a matrix. How can a matrix represent a system of linear equations? So I can represent the system of linear equations 3y equals 1 minus 2x, 4x equals 10 plus 2y using a matrix. Okay? So a matrix is a rectangular array of values. A matrix allows you to keep track of the coefficients and constants in a system of equations without writing the variables. So to use a matrix to represent a linear system of equations, the equations must first be written in standard form. So basically that ax plus by equals c, that's the form you need to write these in, okay? So once I do that, I get 2x plus 3y equals 1 and 4x minus 2y equals 10. Okay. A coefficient matrix, coefficients of the variables in the system of equations. So basically I take these coefficients, the 2 and the 4, they become this column, and then the 3 and the negative 2, they become this column. Always include the positive or negative signs, especially if they're negative. You don't actually have to put plus 3, but make sure the minus signs or the subtraction or the negative signs are in front of the numbers that they're actually in front of in your matrix. Okay. An augmented matrix shows all coefficients and constants in the system of equations. So a dotted line separates the variable terms from the constant terms. So here's my x coefficients, my y coefficients, and then the constants, the equals, okay? Dimensions of a matrix are R by C, the rows by the columns. So this is, there are 2 rows, this first row, second row, and then 3 columns. Okay. So this system of equations can be represented by this matrix, this augmented matrix. I can go backwards, of course. I can do matrix to a system, and I can do systems to linear equations. So here I have a system of linear equations in 3 variables. Okay? I have my x's, my y's, my z's, and my constants. I can notice that there's no z here, so that's going to be represented by a 0. Okay? So when I do this, I pull out all the coefficients, the constants, and I set it up in a matrix. All my x values, all my y values, all my z values, all my constants. Okay? So let's go ahead and try some out. The first one I have is 3x minus y equals 4 and negative 2x plus 7y equals 20. Okay, so here's my matrix. I'm going to use red for x and blue for my y values. Okay. So looking at this, the first value I have is 3. And then I have a negative 2. So there's my first row. My first column, my second column is my y values. So negative 1 and 7. Then I have this dashed line, and then I'm going to write my constant values, 4 and 20. Let me take a little picture of this. Saves, that's always nice. Okay. Xbox. All right, so when I enter this in, I get 3, negative 1, 4, and then negative 2. You can check your answer, same thing. Letter B, I'm actually going to go backwards. I'm going to write the system of equations for the matrix. So 0 means that it's just a placeholder. So 2y plus 3z equals 4. I have 8x minus 1y minus 2z equals 5. 2x, the 0 is a placeholder, plus 1z equals 9. Here's my system. Example number 5, relate systems of equations and matrices. So an algebra teacher creates the matrix shown to describe an exam, where x represents the number of 2-point questions, y shows the number of 5-point questions, and I want to write the corresponding system of equations that does each equation, and what does each equation represent. So pick 2 variables, x and y. 1x plus 1y equals 19. So x is the number of 2-point questions, y is the number of 5-point questions, so there's a total of 19 of them on the exam. 2x plus 5y equals 50. So 2x is the number of points available from 2-point questions. 5y is the number of points available from 5-point questions, and the exam's worth a total of 50 points. So an algebra teacher creates the matrix shown to describe an exam where x represents the number of 2-point questions and y shows the number of 5-point questions. Okay. What does the matrix 1, 0, 15, 0, 1, 4 mean in terms of this context? Well, this means that this blue number, this blue 1, represents the number of 2-point questions. Well, there must be 15 of them on the exam. And the red 1 represents the number of 5-point questions, so there must be 4 of them on the exam. Okay, I can check that system and make sure it works. It does. So for number 5A, they want us to write a system of equations described by the augmented matrix and describe a real-world situation that could be modeled by the system. So the linear equation could be x plus y equals 10 and 3x plus 2y equals 80. So this could be there are so there's a test, X number of 3-point questions and Y number of 2-point questions for a total of 10 questions on the exam. The second equation would represent the number of 3-point questions plus the number of 2-point questions for a total of 80 points. Could be anything. Doesn't have to be questions on a test. It could be packages of pens, okay, that cost $2 each. Anything like that. Okay. What would the matrix 1, 0, 20, 0, 1, 10 represent in terms of your real world situation? Well, in this case, there would be 1 for 3-point. There are 20 3-point questions and 10 2-point questions on the exam. Okay. For the packages of pens, it would have been 20 packages of blue pens and 10 packages of red pens. Okay. So concept summary in words. A system of linear equations versus a system of linear inequalities. Both have the same variables attached to them. In algebra, we can solve them by graphing or by substitution or by putting them in a matrix. And then we can always graph them as well. And that is the end of Unit 1, Lesson 6.